All right. So I had a question about lab 3, part C, I think it was. And I'll just do it, but change the numbers. So you'll have to do it for yourself with the different numbers. So let me start with the simulation. There's 2 parts. There's the equation part and the simulation part. And let's get this Word document up. That made it worse. Okay. There we go. Okay. And then multi-sim. All right. So we've got a battery, power supply DC. Okay. And the ground. Okay. And then I need resistors 1, 2, 3, 4. So that's under basic resistor. I'll just say 1, 2, 3, and 4. And then I'm going to rotate 4. It doesn't matter what it looks like, it matters how it's connected. So somebody was showing me the sort of the new sort of home version that he had last week. And like if you forget how to rotate, it doesn't matter. It matters how it's connected. So if this resistor were not rotated or something like that, that would be perfectly fine. And I'm going to change these numbers to just not the numbers, just not those numbers. So I'll say 3.45. That sounds like fun. 1.23. So what do I make this 1, 2, 3, 4? That sounds reasonable. And then this one I will make I don't know, 4.56. That sounds like fun. Okay, so I have those, they're all kiloohms, kiloohms, okay, connected. I'll leave it at, well, let me make it 9 volts. Just for fun. I'm just changing the numbers so that I'm not doing the work for you, but I'll do very similar work. Okay, and then the questions were about the voltage across and the current through the 2.87, which was R3. So that's what I'll measure here. So let me get under here a voltmeter, which I'll place in parallel. And let me get an ammeter as well. Why not? And then I'm going to move this back a little bit and put the voltmeter across. And then the ammeter would go in series. So I'm going to delete what I had and then add it back in with the ammeter. Okay. And let's arrow that down a little bit to make a little bit more room. Okay, make it look a little prettier. Doesn't matter if it's pretty or not. And then there is my simulation, 0.981 for a current and 2.295 for a voltage. Okay. And now that is the simulation part. So simulate the circuit, that's the simulation part. Now let's do the theory. So we look and we see we're looking for either series or parallel. Series means that the two resistors must share must have the same current. So I shouldn't use the word share. I don't know what that means. The current that goes through one resistor must go through the other resistor. That is our definition of series. If there's a connection of wire on one side and a connection of wire on the other side, then that is parallel. So the current comes out, the charges come out of the battery and come to this node. And remember that in our picture, if we have made the voltmeter in parallel and the ammeter in series and their ideal meters, they should not affect the circuit. So when I'm going to talk about which way the current goes, we're never going to imagine it going through the meters. Well, we're never going through the voltmeter, but going through the ammeter and having no effect. Okay, so the charge will come out of here, we'll hit this node, some of it will go through this direction, some of it will go down here. Whatever went through one must go through two, it's got no place else to go. So 1 and 2 are in series. So let me do this. Let me snip. And put that over here. Okay. So now it's less confusing. So R1 and R2 are in series, and that is just an addition. But whip out this calculator, and what am I going to do? I'm going to add 3.45 plus 1.23, and that is 4.68. Yes, that seems to make sense. Okay. So now I can make that replacement in normal life. If I weren't stuck here at a computer and recording, then I would just redraw the circuit. But since, am I running? No, I'm not running. Control C, Control, no, paste. There we are. Okay. I'm going to, when I replace two things with one, I see where I came into the combination, where I went out of the combination, and I make it just one resistor. I'm going to get rid of this resistor, have just this resistor, and according to what I just said, this should be 4.68. Again, I would just quickly draw it normally, 4.68. But I'm doing this because this is what I can easily do at the computer. So this is overkill on the simulation side. I only want really the individual or the first one simulated. Anyway, okay, so here we go. So now I have charges come out of the battery, come here to this node, and some go through R6 and some go through R7. There's a connection of wire on this side, a connection of wire on that side. That makes 6 and 7 in parallel. I'm going to say R12, that's the result of combined, that's R6. And R3, the original R3, are in parallel. And what does that give me? So I have the 4.68 and the 2.34 in parallel. And my calculator has that nice reciprocal button, so that's the way I do it. 4.68 reciprocal plus 2.34 reciprocal equals reciprocal 1.56. Try it one more time. It was 4.68 reciprocal plus 2.34 reciprocal equals and a reciprocal, 1.56. Okay, and so now I will make that replacement. So copy this guy, Control-C, copy that. And again, I would normally just draw these on a piece of paper and hand in the piece of paper on a test. That's what I would normally do, but I'm stuck at this computer right now. So I'm getting rid of this guy. I'm getting rid of these, getting rid of my meters. And then I will. So now the what was this? The 1.56. Okay, so I have the 156 and the 456, and they are in series. The current that goes through one must go through the other. So what am I saying here in the original? R123 and R4 are in series. And so that's the 1.56 and the 456. Nope. The 1.56 plus the 4.56, and that's 612. Okay. So one more replacement. Now I'm down to one resistor. Which was 6.12.
You just want to see a screenshot of that.
I don't need, you can draw this on a piece of paper, as I keep saying. So if you want to do it this way, that's fine. If you, and you can turn in the file, you can give me screenshots, you can write it on a piece of paper. However you're comfortable doing it. I'm down to one resistor. So now I can find the current. 9 divided by 6.12, the voltage divided by the resistance gives me the current. And I have an overall current of 1.47. So I'm back here, current out of battery is 1.47 milliamp. This was the kilo ohm, I'll just say. Okay, now take a step back from this 612 to from where it came from. It came from this 1.56 and the 4.56, and I know that they have the same current and that they have the same current as their equivalent. And so these two, 5 and 10 in this picture, those two have a current of 1.47. So I think I was calling this R123 and this R4. And what was I interested in? R3. So I'm interested in the R3. So that's what I'm going to work with. So the current through R123 is the same 1.47. And then that tells me that the voltage of 123 is the resistance 123 times the current 123. And so that is the R123 was the 1.56, right? I think.
Yeah.
Yes, somebody agrees with me. Thank you. And then the current was 1.47. And so that is equal to what? 1.56 times 1.47 is 2.29. And I have in my little simulation up there, the voltage across the R3 is 2.295, so that makes sense. I recovered by equations what I found in the simulation, as I should. And things in parallel have the same voltage. And so if the voltage across the 1, 2, 3 is equal to the voltage across R3. Things in parallel have the same voltage and the same voltage as their equivalent. So if I knew the voltage across the 1, 2, 3, I know the voltage across R3. So the voltage across R3 is, as we just said, 2.29. And then if you know V equals IR, if you know the voltage and the resistance, you can find the current. So the current of 3 is the voltage of 3 divided by the resistance of 3. And so that's the 2.29 divided by 2.34, and that is 2.29 divided by 2.34. I'm getting 0.978, I'll say. And I compare that to what I got in the simulation, 0.981, so I'm close enough. So this was the lab 3C. And that I just changed all the numbers, so you just have to do what I did, but with different numbers, and you should be fine. What's in lab 4 has like maybe 1 or 2 more forward steps of simplifying the circuit because there are more resistors. But I usually don't have more backward steps than this. What you got to watch is if there's usually one that's easy. Let me have a quick peek at lab 4. So let me go back. Unit 4. I guess it's part C again. It's a bigger mess of resistors, but certain of them are sort of easy. R4 and R8 in this picture are easy to deal with because they see the full current. The current comes out of, in this case, the 12, and it splits up, and some goes through 1, and whatever went through 1 went through 2, and some of it goes through 3, and then they all get back together and go through 4. And then it splits up again, and some goes through 5, and some goes through 6, 7, and then they get together again and go through 8. So when you got it down to 1 resistor and find a current, that is the current for R8, that is the current for R4. And that's one of the resistors I asked about. So that one is fairly simple. I have some people, I don't know why, think the voltage is always 12. And that's not correct. It's not everybody sees, almost nobody sees the full voltage except the final equivalent resistance that sees the full 12 volts. But usually you have to go to get home to go out of the battery and come back home, you must use up all 12 of your volts, but you have to split it between the various things you have to do. So not each resistor sees the 12 volts. That's not the way it works. questions or other questions? Other questions, other parts of the lab you want me to go over? No, nobody. Okay. So. Anyway, well, that's on the recording, so you can watch it over and over again and just do it, but with different numbers for lab 3. And lab 4 has maybe a couple more steps, but is the same game for the most part. All right. I'm going to start talking about adders unless you ask me a question. We do know next week is the test, labs 1 through 4 in class, no online. The online is really just for recording, but some people take advantage of it. But next week, you've got to be here. You have work emergency, I'll deal with you.
Is it not on the computer? It's like a paper?
You can do, no, it's on the computer.
Oh, okay, but it's just saying cross.
Yeah, I like to watch you sweat.
Yeah.
And you can do that calculation on paper.
Okay.
You know, I will hand you, like, the first problem will be the resistor circuit, and I will give it to
Talking about what
you.
you just did?
Yes,
Yeah.
you will, and I will give it to you on a piece of paper. And you can ignore that piece of paper, or you can use that piece of paper to do your equations and just turn it in with your name. And that problem will be worth about 20 points, because there's the simulation. Do you know what to do with voltmeters and ammeters? And then there will be the calculation part and the backward steps. And so between all of that, it's worth about 20 points.
Which you literally just explained to us in the homework. And that's similar to the homework you just went through.
Yes, it will be more than 3C and less than 4C. So it won't be 8 resistors, it won't be 4 resistors, or maybe 6 resistors. Could be 5, could be 7, but probably 6 resistors. And one of the ones I choose is usually easy, like one backward step or not even, and then one's like slightly more involved. But so it takes time, but it can't, so it'll be like a 75-minute test. And then I don't have any plans for using the rest of the time next week. If you want to start half an hour later, so then if you want to ask questions in that first half hour,
I like that.
you like that.
Yeah.
So we'll start late if you're confident. Then come in at 6:45 if you just want to take the test. But I'll do like a review for half an hour in case questions have come up or something like that. So the first problem is about 20 points. You can't make it take the whole time, but you can't like rush through it and get it all wrong either.
How many problems will be on the test?
Say again?
How many problems will be on the test?
I don't remember. You will have will be a sum of products. That's one. So there'll be the resistor, that's for sure. There'll be a sum of products, definitely. There'll be a product of sums, definitely. There'll be at least one Carnot map where you have to do some simplifying. It might have don't care values or it might not. So that's 4. Some binary number stuff. Like here's a digit, interpret it all the different ways. Some question, so that's some interpret binary number stuff. Some question about some power of 2, I usually throw in some kind of question of, you know, if I have, here's some scenario, how many things can I address, or how many different things can I distinguish? And now we're
Like
up to
the
7.
IP stuff?
Yeah, yeah. So that if I were asking about IP, which I won't, but if
Right, yeah.
I would say, you know, there were 32 bits in principle, how many things can I address?
Okay,
And I'm not looking for any kind of, you know, network theory answer where this address refers to blah, and these are not accessible and not used. I'm just looking for 2 to the 32 and get out. So there'd be that kind of a question, probably something with fractions in a binary number. Maybe a quick like 16th complement or something like that.
what's that mean? Are you talking about like, when we did the decimal binary numbers?
When now I lost count, but who the hell cares? What do I mean? What do I mean by what do I mean? All right. Unit. So this was the 16's complement or the 10's
Oh, okay.
complement, that thing. So if you know the tricks, it's easy points. And what was on not part C, that was some resistor thing. Part B. I usually ask some question in here. Some people get the signed part wrong, get it right. I usually ask some decimal number part. The fraction there is the hard part, don't get it. And then I usually ask some 2 to the blah question. And then I said from lab 2, I tend to ask sum of products, product of sums. Lab 3, I'll tend to ask a Carnot map. You'll tend to get a resistor. There will be something with multiplexers and demultiplexers. I will probably ask at least one or two vocab questions about multiplexers, demultiplexers, and then I will tend to ask one operate a circuit kind of question with multiplexers, demultiplexers, and something from the book, chapters 1 through 4. Maybe a vocab question from the book, maybe like a give me 3 sentences kind of a thing from the book. And you're allowed to, you know, have your electronic copy of the book and whatever summaries you wrote. So you don't have to have the book memorized or anything. If you've read the book and have quick access to it, you should be fine on that question. That's what's on the test. Any questions? So lab 5, not on the test. That's what we're starting. Okay. Okay. Adders. Okay. Adding. Slideshow from the beginning. Okay, so we're going to make an adder, and then we'll also talk about digital to analog converters. Okay. So we know we played the binary number game, and so we know that we're doing same positional weighting we do in decimal numbers, but we're just doing it in binary. So in binary, we have 1s and 0s, 2 digits instead of 10. But all of our other ideas that we know from math still apply. We talk about the powers in decimal, the powers of 10, and then we say that a digit has a place in the number, and that if the place in the number represents the highest power of 10, we will say that that is the most significant digit. And then if it's a whole number, then the ones place will be the least significant. Doesn't mean it's not important or anything like that. It just means the power of, in this case, 10, or when we get the binary, the power of 2. So I think, where is it? Somewhere in lab 4, there's a digital version of a multiplexer, and it's got, and then the address is A and B, and I asked you between A and B, which one's more significant. A and B sort of play almost an equal role in the circuit, and that's not what the word means in this context, but we are using A and B to represent a number. That means one of them is the ones place and one of them is the twos place, and the twos place, whichever one it is more significant. Not more important in the circuit, but more significant, just meaning the higher power of 2. Okay, and we know from early lecture 1 playing with numbers that we can add them, and then if in a given position your addition exceeds the base, then you carry over, and that will be the same with binary as well. Just some vocabulary. The action you perform is known as an operation. The data that you act on is an operand. And then we're going to be dealing with addition of binary numbers. And so what we're going to be talking about is binary in 2 senses. The operands, the data will be binary numbers, and then the operation will involve 2 pieces of data. And so it will be, that's binary in another sense. So if the operation is, or operator, and takes 2 pieces of data, it's said to be binary. And then if the operands use just ones and zeros, high and low, then that is also binary. So this addition is binary in two senses. The operator is binary, and the data we're acting on is binary. Okay, so when we add 2 numbers and with our positional weighting, then we can get only a handful of scenarios. You will have, ultimately, in a given position, you will have 3 inputs. So overall, I'm adding 2 numbers, but at a given position of a given digit, I might have 3 inputs, and that would be that the binary digit in that place for each number, and any carry that came from a previous. So overall, my addition is binary with, but I may end up, if I'm looking at it in one position of the addition, depending on how, if I'm thinking of it that way as position by position, then I end up with 3 inputs because of the carrying from another place. I don't have to think of it that way. We just tend to think of it that way. But okay. So we're going to talk about the logic of addition. So we're going to take those inputs, we're going to look at a given position, look at those inputs, look at the outputs for those inputs, and create the truth tables of addition. Okay, so we're going to be in a given position in our number. We're going to have 2 or 3 inputs, depending if we're considering the carry or not, and then 2 outputs. The number that goes in our answer in that same position, and any carrying out to the next higher position. So we're going to have 3 inputs. When we do what's called full addition, we will have 3 inputs, and two outputs. So let's do, before we do full addition, let's do half addition. Let's just add A and B, not worry about any carrying. So if you just have A and B, there are two bits. There's the A bit and the B bit. And so there are 2 to the 4, sorry, 2 to the 2 combinations or 4 combinations, 0, 0, 0, 1, 1, 0, and 1, 1. And there were 2 outputs of addition, the sum and then the carry out to a higher place. So if I had 0 and 0, I get 0 with no carry. If I have 0 and 1, I get 1 and no carry. If I add 1 and 0, I get 1 and no carry. And if I add 1 and 1, I get a 0 in that position and I carry. That is. So that's the truth table of addition without any carrying in. We always have to talk about carrying out, but right now we're ignoring the carry in. So maybe we're doing the ones place, or maybe we're just doing half the job. Okay, and you know how to build these. The sum is just an excluded or, one or the other, but not both. So if you wondered what the hell that excluded or thing was, well, right there it is, it's addition. And carry out is an and right now. All right, so we know how to build this. There's an excluded or and an and, easy enough. So there is the half adder logic. I have some inputs A and B. If I really wanted to operate it, A and B would be connected to switches and the switches to batteries. The outputs might be connected to probes, but here's the logic of it. An excluded or and an and. When you grab an excluded or, make sure you don't have a little circle on the end because that's an excluded nor, and that's different. In fact, it's the opposite. Also for and, don't grab it. The and, it's easy because usually you get the list and it's alphabetical, and comes before nan, so you're usually fine on the and unless you're coming up from the bottom. But the problem with the excluded or is alphabetically you run into excluded nor before you run into excluded or, and you grab the first thing that looks kind of right and it's not the right thing. So be careful. Okay. So now we want to go to a full adder, and there are 2 approaches. I can add the digits A and B and then add that result to the carrying. So I can get full addition by having 2 half additions, or I can just look at the full on truth table for the 3 inputs. And we're going to do both. So now we're making a full adder. So here's just straight on the full adder truth table. So there's a carry in from some previous position, and the A in that position and the B in that position, and 3 inputs, 2 to the 3 is 8 possibilities, all the way from 0, 0, 0 to 1, 1, 1. And here's the sum, and here's the carry out. So if I added 0 and 1 and 0, I would get a 1 and no carry. If I added 0 and 1 and 1, I would get a 0 and a carry. And if I added 1 and 1 and 1 at the bottom, I would get 1 and a carry. I can build this, I can achieve that logic by 2 half adders. Here's my excluded or and another excluded or and excluded or and. So my red dashed box is a half adder and a half adder. So I can add A and B, and then that answer is from the excluded or. I can add that to the carry in of C into my second half adder. The overall, the sum out of the second half adder is the sum. And then I have 2 additions. I did two operand additions, 2 half additions. and either one of those additions might have carried. And so I or those two additions, or the carry out of those two additions. If one or the other of those additions carried, then overall I'm carrying. So this is full addition from two half additions, and you or the carry outs. Okay. Now I'm going to go back to the full adder truth table and imagine building that, but I want to try and simplify first. So I'm going to put it in a Carnot map. Here is the sum output of the Carnot map. So I have A and B and the carrying in. And so in our Carnot map, if you remember, we take two inputs and we take them down in rows, and then any other additional output inputs we take across in columns. And here is my outputs for the addition. Is there any simplification? He shakes his head no. Multiple people shake their head no. Because we asked this question before, we called it parity. And so addition and parity are similar looking, that they have this sort of checkerboard pattern, and there was no simplification. So addition has this checkerboard pattern the same way parity did, and it doesn't simplify. Now they have in multisim, and this is an excluded OR, they have an excluded OR. Yes, they have an excluded OR. They have two input excluded ORs, three input excluded ORs. So you can make this look simple, but it's just hiding the complexity. This really doesn't simplify, but it's something, it's a pattern that pops up a lot. So they make it, they say, oh, here's a gate and you can use this gate, so you can make it seem easy, but it's not a real at the transistor level simplification. It doesn't save you space or energy or anything like that. Okay. So, but we know that it's a simplification. We know that it's an excluded OR. It was the same as parity. There's no simplification. It's that checkerboard pattern in the Carnot map. So there are no groups of ones to lead simplification. So here's if we wrote out a two input excluded OR, here's what it would look like, and here's what it looks like if you use the gate. And so this looks simpler, but it's just a notational simplification, not a genuine transistor when you build it simplification. Okay, so that's me saying that it's not a real simplification. Okay. Now it's still simpler to build the full adder from scratch rather than making it two half adders. That will be a simplification. So making a full adder from two half adders is it's taking us out of our way. But when you do go to the full three input, to the full adder with the three inputs, the sum output does not simplify because it was that checkerboard pattern. Okay, here is the carry out in Carnot map. And when do you carry? Anytime you have at least two ones, you're going to carry. And so that is, if you have two ones or three ones, you know you're going to carry in that position you're considering. And that is the majority rules. So before we just said, we pretended we were voting or something like that and said, oh, let's have a majority rules. And we figured out what that truth table looked like. But now we know that it's also, majority rules is also carrying. So the full adder carrying is majority rules. And so you remember this game, if you remember from way back when in unit 3, we said there was that one bit that everybody wanted to get together with, ABC. And there it is. You see that that 1, 1 belongs to the green group and the red group and the blue group. So here is the after playing around with simplifying the carry out. And here's our majority rules. 2 input and 2 input and 2 input and 3 input or. And this thing that looks notationally simple, but isn't really the 3 input excluded or. So while the carry out looks complicated there and the sum looks simple there, it's actually the reverse. Because hidden in here are nots and ands and ors and blah, all sorts of complicated stuff. Okay. So taking it from scratch and doing the full adder from scratch is better than the 2 half adders. Okay. And now we have how to add one position of a digit. So this is, and they're just going to give you a box. In multi-sim, there's going to be a box called a full adder. It's going to have 3 inputs and 2 outputs. And so you're not even going to have to build this. It's just going to be a box, like a sub-circuit, like you made in one circuit, a sub-circuit or a box that has 3 things in and 2 out, and this is what's inside. Okay. So now we want to add more than one position. So all of that whole thing, that was one position in the digit. Now we want to put the positions, the different positions together. And so one of the inputs of a position is a carry in, and one of the outputs is a carry out, and then you have the next position over, and the carry out of the position you just finished becomes the carry in of the next position. And this is known as rippling. And so we make a ripple adder. So here's this box that I told you about. It's got A, B, and CI carry in, A and B. And here's another full adder, A, B, and carry in. And then there are 2 outputs, a sigma and a carry out, sigma and a carry out. This is an old picture from an old version of multisim, so it doesn't quite look like this, but it's a box with 3 things coming in and 2 things going out. And the way that you make a ripple adder is you connect the carry out of, say, the 1's place to the carry in of the 2's place. So this is a 2-bit ripple adder. You have to make a 4-bit ripple adder in lab 5. So how many inputs are you going to have? And you have to operate it, so you need switches and batteries and all that. You're going to add A, the number A has 4 bits, the number B has 4 bits. So you're going to need at least 8 switches. So you'll love me when this is done. And you're going to have at least 4 outputs, the sums. And all right, so that's what that's going to look like. And if you have that ripple adding, then you can, that has the logic of addition. And so a ripple adder is an adder. It's logically addition, so we can now do addition. A problem can arise in that if you have some kind of addition that has lots of carrying, then you must finish the first addition before you can really start the second addition, and then you must finish the second before you can really start the third, and so on. And so it can take, if you have a very long word, the word is how long your numbers are. Common architectures these days are like 32 and 64, so you might have a 64-bit word, some integer that's 64 bits or something like that. And so if you're going to make a ripple adder, then you've got to go to the, get the ones place settled before you go to the twos place, get the twos place settled before you go to the fours, get the fours place settled before you go to the eights place. Okay. Now, that's if we make a ripple adder. So that's the problem with a ripple adder, is it's going to take too long to do that. Even though computers are very fast, we want them to be as fast as they can be. And to do 64 of these little additions along the way and get them all settled, we are trying to do stuff. What is a speed these days of computer processors? Very good. Say what?
I'd say a joke, fast.
Fast, okay. They're in gigahertz range? Yes. Yes. Built a computer over the summer and you're supposed to answer that question. So speeds are in the gigahertz, around 3 or something like that. And so that means you are doing like 10 to the like 9, or if gigahertz is 10 to the 9, right? Kilo is 10 to the 3, mega is 10 to the 6, giga is 10 to the 9. And you're trying to do that many things, you're trying to do 10 to the 9 things per second. So the things you're doing are less than 10 to the 9th of a 10 to the minus 9th of a second. You're trying to do something in a fraction of a nanosecond. And now I'm trying to do also, if I'm making a ripple adder, I'm trying to do 64 little additions within my part of a nanosecond. So that doesn't, so this is logically correct, but it's not what we really do. It'll be good enough for us because we're just going to do logically correct, but it's bad engineering because we'll run out of time. If we did addition this way, we would run out of time. But addition is really just some kind of logic. And so it's just a truth table. And so you could just build some crazy big truth table and simplify it and build the thing, and that would run faster. So we don't have to do addition by go to the ones place and get the answer, and then go to the twos place and get the answer, and go to the fours place and get the answer. We don't have to add that way. That's there every once in a while you run into some genius who knows how to add very large numbers or multiply very large numbers, and they don't use the technique that you learned in 3rd or 4th grade. What you learn in 3rd or 4th grade works and is logically correct and gets you the answer. If you don't care, then it takes too long. But that's not what we're going to have our computers do. But it's what we're going to build in lab because it'll be good enough for us. But you should at least understand that there is a problem. Okay. So it is this timing problem that, strictly speaking, I may have a lot of carrying and I gotta wait. I gotta get the ones before I get the twos, before I get the threes. That's the problem with ripple adding. And we say there, so it's logically correct. Ripple addition is logically correct, but it has a problem with a timing problem that we won't get the addition completed and or completely accurate and complete in time if the word gets too big. So if something works, but if you change the size of it, it stops working, no longer works, then we say that it does not scale. So if you have a solution, but changing the size of your problem makes your solution fail, then you have a scaling issue. Your solution does not scale. And so ripple adders do not scale. And that is a generic thing in computer science. There are lots of solutions to things that don't scale. So we were just talking about the word size in a processor. What if you went from 8-bit words to 16-bit words to 32-bit words to 64-bit words? If you were in a database, can you have more and more records? Does that throw off what you were doing in your database? If you have computer networks, if you have too many computers on your network, does that throw off your solution? Does your solution scale? So all through IT and all through computer science, there are scaling problems. And we're going to ignore it and just do ripple addition because it's logically correct. But I may throw a question here, what's the problem with ripple adders? And you will just throw back a quick answer, they don't scale. Okay. But again, addition is just a combinatorial problem. 3 + 4 is 7. It doesn't require, it's not, if you read the book, you talked about finite state machines, and they depend not only on the input, but on the state of the system. So there'll be some state of the system, and then in addition, some input, and that will change how things happen or what happens. And he gives us a simple little example of maybe a pen that you click, and if your input is the clicking, and the state is whether the little nub is out or in, and so the input, the click is the same, but you get this toggling effect. If the point was out, it will retract. If it was retracted, it will come out. That depends on the state. Addition doesn't depend on the state. It's not like 3 + 4 is 7 because we are turned on, and if we were turned off, it would be some other answer. So addition is just logical, just combinatorial, just a truth table, and we know how to build a truth table. We've been doing it for like 4 weeks now, or 3 weeks now. But you've seen truth tables, and now imagine a truth table where I'm going to add 2 64-bit numbers. I'm going to add 2 64-bit numbers. Then, of course, I have 128 bits coming in as inputs. And then my truth table is going to be 2 to the 128 rows of my truth table. So that's going to be complicated. And you could imagine, so we're not going to write out such a truth table. I don't want to think about it. But you can imagine that there's some like OR gate with a ton of crap coming into it, or a NOT gate feeding a ton of crap. And so that is the problem with the purely logical solution, other than getting the logical solution. But there's an engineering problem with a pure logical solution, and that is that you may have what are called fan in and fan out problems, so that you have to have too many things coming into you or have too many things coming out of you, and that it has engineering issues. It's logically correct, but there are engineering issues of your current is being eaten up by too many things. And so then sort of that's why there are computer engineers. You're training to be a computer scientist or a software engineer or an IT person, but the people who make processors deal with this, like the electronics of not just the logic side, but the electronics that are behind the logic, and it's not always easy. Okay. All right. If we want to subtract, we know how to do this. We could say there are other ways. We talked about negative numbers, and we talked about 2's complement, and I we based our definition, if you recall, we based our definition of 2's complement of negative numbers, we based it on addition. Now we have adders, and the brilliance of defining our negative numbers by using 2's complement is that we do not have to rebuild, we don't have to build a subtractor. We interpret our numbers as positive and negative numbers based on addition, and then we have addition. We don't need a new device that subtracts. If we did it some other way, if we had some other representation, then we'd have to have all these cases. What if I'm adding positive to positive? What if I'm adding positive to negative? And the first one's positive and the second one's negative, or the first one's negative and the first one's positive, and which one's bigger? And I'd have all sorts of scenarios, but I don't need all those scenarios because everything's based on addition. So everything was sort of reverse engineered from addition. So all we need to do is know how to apply 2's complement into a circuit. And then we will have subtraction. So we don't have to build a subtractor, we have to build like a 2's complement generator. So if we didn't do 2's complement, we'd have all this cases and complication, but we used 2's complement to avoid all that. Now all we have to do is build something that will exchange ones and zeros. If I want to make a number negative, I have to exchange ones and zeros and add a 1 in the ones place. I know how to add a 1 because I have an adder. And the thing that exchanges ones and zeros, we will see, or you will see, or maybe you'll remember when it comes up in lab 5, is yet again an excluded OR. Our lovely excluded OR comes up so often. Okay. So we know this game. Take those ones and zeros, exchange them, add a 1 in the ones place. That's a negative number. Okay. So you have to build in lab 5, you have to build a half adder. It's on the lab copying. You have to build a full adder from 2 half adders. It's on the lab builder. Then you start using the little boxes of full adder. You have to build a ripple adder. Okay, I told you that's a pain in the ass with 8 switches and yada, yada, yada. You'll ask me at some point to draw that. I don't know where to start. Tell me what it looks like. Maybe you'll ask tonight. I don't know. And then you have to turn it into a subtractor. Okay. Digital to analog converter. So this is a different story. So we want computers to, if you had architecture, you have to have a computer, you have to have some kind of processor. And we've been doing sort of, if we have an adder, that's kind of an elementary CPU. The next week, not next week, next week's the test, but the next unit we do is memory. We need memory to have a computer. And then we need input and output. If we have input, output, some kind of processing control, and so control and processor depends. Sometimes you think of them as 1, sometimes you think of them as 2, depending on how you think. And memory and input and output. The digital to analog converter is about output. So I have some digital thing, and I want to, and my internal world of the computer is digital, but the outside world is analog. And so to get my stuff inside my computer to outside, to play a sound, to have a pixel on my monitor, what have you, I need a digital to analog converter. Okay, so if I want to go from digital, the inside of the computer world, to the outside world, then I want a digital to analog converter. And we're just going to play games with resistors, switches and resistors, and we will make this digital to analog converter. So I'm never going to go pure analog. I'm just going to go to some kind of pseudo analog. And analog has all the numbers in between. So we've been dealing with highs and lows, let's say 5s and 0s. So if we want to go towards analog, we want to start filling in the middle. So the first thing you fill in is half, is 2.5. And then you start filling in quarters and 3/4 and so on. So we're going to make binary fractions. Oh, good, we've already played with binary fractions. So I want to put in a binary number that corresponds to a fraction, and then I want that fraction of the whole. So if I have a 1-bit digital to analog converter, if I put in a 0, I want 0. And if I put in a 1, that corresponds to a half, I want half the voltage. So if I make a circuit where if I put in a low, I get nothing, and if I put in a high, I get half of my reference voltage, I have a 1-bit digital to analog converter. Doesn't sound very interesting, but then we will add another bit and another bit and another bit, and then we will be able to get a quasi-continuum of outputs. Okay, so you just have to remember your binary fraction stuff, which of course you do, and you will next week, certainly, because it'll be on the test. So again, we remember that in binary fractions, the powers of 2 are negative. So after the dot, the first place is the halves place, then the quarters place, then the eighths place, going on down the line. Okay, and now we're going to play, so we know what our inputs are going to be, highs and lows. We know what we think they're going to represent. They're going to represent some fraction, and now we want to get that fraction of our reference voltage out, and we're going to do that by playing with resistors. Okay. So we've seen this game. I have 10 volts. I'm going to send it through 2 resistors. Those resistors right now happen to be in series, and so there's going to be some fraction of the voltage across one of the resistors. So right now I have sort of a third of the voltage is, if I measure across the 1 kilo ohm resistor there, I'm getting about a third of my voltage. Okay, that's just reminding you of resistors. Now let's get the fractions we want, like 1/2, 1/4, 3/4. And then, and some of the times we're going to have series, and some of the times we're going to have parallel. And you know these rules, that's where we started today. We started looking over our resistors in series and parallel. Okay. So I'm going to start off with what's called a voltage divider, but a voltage divider is also, another name for it would be a 1-bit digital to analog converter. Here it is. I have in this case, in this circuit, I have a 5-volt reference voltage. So my fractions are going to be fractions of 5. I have 2 1 kilo ohm resistors in series. I have a switch corresponding to my 1-bit input. If that 1-bit input is high, if it's getting that 5 volts, then that 5 volts goes through the 2 1 kilo ohm resistors that are in series, and I use up half my voltage on the first one and half my voltage on the second one. And if I measure my voltage across the second one, across the bottom one, that is half of my voltage. So if I put in a 1, and remember, I'm thinking of this input, I'm thinking of it as a binary, as a 1-bit fraction. A 1-bit fraction is .1 or .0. .1, after the dot, the first thing is a halves place. So I want a half if I have a 1, and I want a 0 otherwise. So here is the half. And if I put nothing in there, well, if I put nothing in there, I get nothing out. There's my 0. So this is a 1-bit digital to analog converter. It's also called a voltage divider because it divided my voltage. Okay. Now, I'm going to make a 2-bit version. And you have to make in lab a 3-bit version. So pay attention to what stays the same and what's new. I'm going to make a 2-bit digital to analog converter next. So the first thing I need to do is have 2 inputs. So I'm going to add another switch that's connected to the battery. I'm going to add another resistor. That's going to connect to that switch. So this is the 1-bit digital to analog converter. Here's the 2-bit. 1-bit, 2-bit. I added a switch. I added a resistor. I didn't touch the other stuff. The 1 kilo ohm and the 1 kilo ohm that were there in the beginning, they're still there. I added a new switch. I added a new resistor. Now I have to show you that this is a 2-bit digital to analog converter. Okay. Well, there are 4 possibilities. I'm putting in 2 bits. So it's just like a truth table-y kind of a thing, although the outputs are not highs and lows, the outputs are fractions. But still, the input is binary and digital. So the inputs are low, 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 high, high, low, and high, high. And so one of them better be, low, low better be 0. High, high as a digital fraction is a half and a quarter, which is 3/4. And then I should have a quarter and 3/4 and a half. So I should have 0, I should have a quarter, I should have a half, I should have 3/4. If this makes sense as a 2-bit digital to analog converter, those are the fractions I'm looking for. Those are my 2-bit fractions. 0, a quarter, a half, 3/4. Here's the easy one, 0, 0. So nothing's going in, so nothing's coming out. So the battery, here's the high end of my battery. It comes out to B, but it's not connected to anything. It comes out to A, it's not connected to anything. The inputs A and B are low. And so there's just no voltage into the circuit, so the output is 0. So I have a 0. I'm a quarter of the way there. All right, so I have 4 states to tell you about. There's the easy trivial one. Okay, I'm making B high. And note that B is the one with the new resistor that I made to be a half. I didn't change the other 2 original resistors, but I added my new resistor was a half. And when B is high, what does the circuit look like? I come out of the battery and I go through B and I go through the half, and then I hit this node. And I'm going to ignore I'm going to ignore the voltmeter. Ideal voltmeters, I don't think of them as part of the circuit. So I come out of the battery, I go through B, switch B, I go through the half a kilo ohm resistor, and then I come to this junction, and part of me goes through this one, and part of me goes through that one. So I have two 1 kilo ohm resistors in parallel. If you play your game, play this crazy game, it's almost trivial, but I'll show it to you just to prove it. 1 1 on plus 1 1 on equals 1 on, it's a half. So that was a silly game, okay. So those, I came through the high part of the battery, I went through switch B, I went through the half kilo ohm, then these two resistors, the way that my switches are right now, these two resistors are in parallel. For this setting, for this switch setting, those two resistors are in parallel. Two 1 kilo ohm resistors in parallel give me a half, give me the equivalent of a half. So the combination of these two is a half. So I went through a half. I have another half to go through, or the equivalent of a half. And so I've used up half my voltage to go through the first half a kilo ohm. And so the voltage at that stage is half of my reference voltage. So the new switch is a half. The switch then is a half has changed. Before, switch A was a half. It was the only switch. Now switch B, the new switch, it's now the half. Okay. So now I have two. I have 0 0, and I have 0, and I have a half. I still need a quarter and 3/4. This is me saying what I just said. Those two resistors were in parallel. Their equivalent is a half, and so I use up half. Now let's do A is high and B is low. Okay. So I come through A. B is low. I come out of the battery. I come through A. I come through this 1 kilo ohm. Now I have to go home to the other side of the battery, to the ground. I have two paths. Where's my mouse? There, I can go through this 1 kilo ohm to get to the ground, or I can go through this half to get to the ground. So I came through A, I had to go through this top 1 kilo ohm, this half, and this one over here are in parallel. There's a wire connection on one side. There it is. There's this wire connection on this side. There's a wire connection on the other side. There it is. I've told you, I don't know how many times, that resistors in parallel do not have to look like they're parallel in the circuit. Here's proof of that. It's about how they're connected. There's a connection of wire on one side, there's a connection of wire on the other side, and I have that. This and that are in parallel. These two look more like they're in parallel, you know, by our sort of standard, oh, there they are, sort of next to each other. But it's these two that are in parallel right now. And if I do 1 1/2, I play my game on my calculator, clear it out. Here's 1 reciprocal plus 0.5 reciprocal equals reciprocal, I get a third. So that equivalent is a third. So this guy and this guy is a third. So I had to go through a 1, and then after that, there's a third. So altogether, there are 4 thirds. I have gone through 3 thirds. I've gone through 1, which is 3 thirds. So I've gone through 3/4 of what I have to do, and I have 1/4 of my energy left. So there's the half and the 1, they're in parallel. That equivalent is a third. I have this, I've gone through 3 times as much as down here. And so I've used up 3/4 of my energy. I have 1/4 of my energy left. So I have 1/4. I had 0, I had 1/2, I have 1/4. If I get 3/4, I win. So high. Now the two that look to you like they're in parallel are in parallel because there's a wire connection here and there's a wire connection here. So now these top two are in parallel. And so now these are the third. And here's the one. So before it went through one and then it went through the third. Now it goes through the third and then the one. So just the flip of what we had previously. And so it is the 3/4. And so I have the what this is the 2-bit digital to analog converter. So all this series parallel, blah, 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 that was just me convincing you that I got the fractions I want to get. Let's go back. Here's the 1-bit, 1 switch, 2 resistors. And here's the 2-bit. New switch, add in a resistor, don't change the old stuff. Here's the 1, here's the 1, they didn't change. Here's the A, it didn't change. Here's the new switch B, here's the new resistor. Connect to where the voltmeter was. You have to build a 3-bit. To my mind, there are only 2 possibilities, and you're going to do an experiment. You might see more possibilities than I do, but I think if I see what happened from 1, the way I went from 1 to 2, if I follow the pattern and go to 3, then I add a switch, I add a resistor, and the question is, what's the resistor? And if you ask me, if I'm following the pattern, I think I can only think, I mean, strictly speaking, mathematically, you could think of an infinite number of choices. Yeah, whatever. Shut up, mathematicians. There are 2 obvious, in my mind, choices. You make one, you see if you get the fractions you want, and if you don't, then it's the other one. If you don't see the pattern, then that's a bigger problem. But I hope I just tried to enforce what the pattern is here. I'm going to leave it as an experiment. You're going to try it, see, and what are you expecting to get? A 3-bit digital to analog converter. So you're expecting 3-bit fractions. What are 3-bit fractions? 1/8, 1/4, 3/8, 1/2, etc. You're expecting all the 8ths from 0/8 to 7/8. Of what? Of the reference voltage, whatever it is. In this case, it's 5. You want to make your life easier, then make the reference voltage, I don't know, 8. If the reference voltage was 8 and you're expecting 8ths, then you're expecting 0, 1, 2, 3, 4, 5, 6, 7. I'm not that smart. I would never do that. Okay, so that's me saying what I had to say this week. So it's time for you to either start asking questions again for the recording, or I can stop the recording and answer individual questions, or some of you will just run away. Any questions for the recording? Have you looked at a part of the lab and you say, I don't even know what you want?
Might be answering that next week.
All right, well, you have half an hour next week, so
Yeah.
you have an hour and a half this week or something.
I think we pull the lab back up.
I'm gonna pull the line back up and see if you can come up with a question.
Yeah, right.
we did there's sum of products, product of sums, there's a Carnot map. Maybe may have don't care values, it may not. And then multiplexers and demultiplexers and binary numbers.
I don't know if it's just me, but like, I have no idea what sum of product and product of sum is, like, they're like the same thing. I think.
Okay, well, they're not, but they're similar looking, they're easy to confuse.
Yeah, that's kind of like what I meant.
Okay, so where was that? We can,
I think it was two.
unit 2, yes, and probably part B, I think. Maybe part B. Yeah, here's part B. Okay, so I'm going to make up, as I did before, change it to a different problem. So here's how I usually make a different problem. Come over to scientific and do something like crazy, like, I don't know, 42 degrees or something like that, and take the sine of it. Who cares? Okay. And then I'm going to multiply it by 2 raised to the 8th. And there's a 171. Okay, so I like 171. Why not? And that's just me, my crazy method of generating problems. So what was that? 171. Okay, so 1010 1011. So that's going to be my new output. And where is it? 1010 and 1011. Okay. So now here's the easy part, the vocab. Another term for sum of products is min term. Another term for the product of sums is max term. So I'm just telling you those answers. And here I'm going to give you the answer, but for this different problem. Okay, so in sum of products, I focus on the ones. And I use and expressions. I can sort of put my expressions here and put them together down here, or I can just work down here. Do you want me to break it down slower, or?
No, you can go like pretty quick through it. I just kind of get confused sometimes.
Okay, so we're focusing on the ones, and we're going to, in the sum of products, you start with the product, and the product is an and. So it's the and, logically the and looks like a product, sort of acts like a product. And ands want ones. To get a 1 out of it, the unique thing of an AND gate is when you get a 1 out of it, everything else gives you a 0 out of it. And the way you get a 1 out of it is when all the inputs are ones. Yes or no? If I want to write an expression for this output, and I'm going to say that that is A prime, B prime, C prime, because that thing, that AND gate gives you a 1 for A low, B low, and C low, and is 0 all the other times. Because an AND gate only gets you a 1 when all the inputs are 1. And so, but I had a 0, 0, and 0. So I had to invert this, invert this, invert this.
Yeah.
So I had to, before I got to the AND gate, I had to invert all of these so that they would be ones.
So does the min term always go after the ones, or can also go after zeros?
The min term is just another word for sum of products, if we're not simplifying. And it means we're going after the ones.
Okay, and then the other one, max term goes after zeros.
Yes. Yeah. And so right now I'm doing the ones. And so that first one, I want to write an and expression. And I'm saying in my sort of shortcutted vocabulary, ands want ones. And so because I have zeros, I will prime them. When I see zeros, I will prime them. When I have ones, I'll keep them. When I have zeros, I'll prime them. So that first one was A prime, B prime, and C prime. And then here comes the sum part, a plus, and then now I'm here. And the B is a 1, but the A and the C are zeros. So the zeros I prime and the ones I don't prime. A prime, B, C prime. That was here. A, B, C, but the A and the C were 0, so I prime them. Here's my next one. It is, the A is a 1, so I keep it. The B and the C are zeros, I prime them. And I don't need any fancy prime, just a single quote's good enough. That was this guy. This guy is A, B, C prime. And the final one down there at the bottom was ABC. So
you would just do the with the zeros for the max term?
yeah, then
Yeah,
we're
okay.
focused
That
on the
makes sense.
zeros. So let's focus on the zeros. And the 0, you write an OR expression. And the place where an OR is unique is when you're feeding in all zeros. An OR gives you, mostly it gives you a 1 output. The one time it gives you a 0 output is when you put in all zeros. If any of the inputs of an OR is high, the output is high. So the unique thing in an OR is when it's all the inputs are 0. So if the AND gate wanted all 1s, the OR gate wants all zeros. And so here it is, A is 0, B is 0, C is not. So it's the C now that gets primed.
Oh, you write it out like that too?
And you write them out with, that is the, you make the sums first, and then you make a product out of them. So this is the one where you need, when you're writing the expression, you need the parentheses. Here's the next one. The A has a 0, it wants zeros. The B and the C are 1s, so they need to be primed. That was this guy. And this guy, the A and the C need to be primed. So the first guy, I'm making AND gates. I make AND gates. I focus on the 1s. I'm working with ANDs. The ANDs want 1s. So if I see zeros, I prime them. In the max term, in the product of sums, I'm making OR expressions. The ORs want zeros. So when I see 1s, I prime them. That is the game. But it's easy to get wrong. But you will have, I will have a truth table and say, give me the sum of products, and I will have a truth table and give me the product of sums. And I will do what I just did. I will do some crazy, nothing to do with it, kind of work over on the calculator, and come up with 1s and 0s. So that's that game. And then maybe I might say build it. And I gave you something with switches. So that's easy enough. And then this is, here you would need, I gave you something with switches and knots already. And then this would be 5 3-input ANDs. And then they would lead into a 5-input OR at the end. Whereas this would be 3-input ORs, going into a 3-input AND at the end.
I'm gonna see if you can do the pairing problem on 3-bit.
Problem. Okay. So the first part is just to understand the definition. I have 4 bits, and I'm going to add a 5th bit to it called the parity bit. And then with those 5 bits, the 5 bits can be zeros or ones. I'm going to ignore the zeros. I'm going to count up the ones, and I want that number, in this case, I think it was to be even. So I'm going to make the new bit, the parity bit, such that the group of 5, when I count up the ones, have always an even number of ones. So this spot right here corresponds to A0, B0, C0, D0. There are no ones there, so that the number of ones currently is 0, which is even. Oops. So I make the parity bit as 0, leaving it even, so I'm happy. I come over here, this next one is A0, B0, C0, D1, so there's 1, 1. And then I'm going to, I want to make it even, so I make the parity bit also a 1, so now there are 2 ones, which is even. Now there's A0, B is 0, C is 1, D is 1. That is 2 ones, that's even. So I make the parity bit as 0. And here I have A is 0, B is 0, C is 1, D is 0. That's 1, 1. I make the parity bit a 1, so that's 2 ones. And we just keep playing this game. A is 0, B is 1, C is 0, D is 0. There's 1, 1. So that parity bit is a 1. Over here, I have A0, B1, C0, D1. That's 2 ones. So I make it a 0. Here I have A0, B1, C1, D1. That's 3 ones. So I make it a 1, which is 4 ones, which is even. And here I have A0, B1, C1, D0. That's 2 ones. So I make this 0. And if I continue filling this in, we get this pattern in our Carnot map. And then we say, is there any simplification? And in Carnot maps, to get to simplify, we look for blocks of 1 that are of size 2 or bigger. The blocks have to be of a power of 2. They can be a size 1, they can be of size 2, they can be of size 4, they can be of size 8, they can overlap. And simplification comes if the group is not size 1. But there are no groups here because there are no ones next to each other. It's like this checkerboard pattern. And even on the wrapping, this guy could wrap around and be next to this guy over here, but he's a 0. He could be wrap around to the guy at the bottom row, but he's a 0. So there's just, even with wrapping, there are no ones next to each other in parity. So, and that's actually what makes it a good error detection scheme is, I mean, it's very complication is what makes it a good error detection scheme. And we saw that that addition has some similar properties. And so there are another checking method is like if you in your data comm course, you might have seen like a checksum. So summing has some of that same kind of properties to it that it's a good check on things. And we'll learn another one later in the semester. So there's just I'm not asking for a simplification, well, because there is none, but you have to say there was no simplification because there are no groups. Anybody come up with any other questions for me?
Yeah,
Like-
for the multiplex B, for the one, I don't find that symbol at the very end. Oh. Circular looking. symbol.
Oh, probe?
That was,
Yeah, they're with the scoreboard, so they're with the voltmeters and the ammeters and the, but that gives me I'll welcome the chance to talk about. Well, first I should find the picture. Let me find the picture.
it's,
Lab for,
well, I was gonna say, if you go to
oh, it's also,
PowerPoint,
oh, it's on the PowerPoint. Yes,
Yeah.
you're right, because I don't tell you what it looks like.
number 28,
Slide 28. is that it?
thank you, that was bothering the hell out of me. That is gonna lead me to another, the sub-circuit question.
Okay,
I'm leading towards here.
all right. So, oh, this guy here is a probe.
Okay,
And probes are under indicators. So
and
where
the
the
second you
voltmeter,
said the voltage there is good.
Yeah.
I mean, I know you're showing other people from the recording.
no, but that gives me, if somebody asks about adders at some point about lab 5, I can show them this doohickey that you're supposed to use with your adder, which is in the same location. Well, let me talk about it for a second, and then we can come back to multiplexers. When you build your adder, your ripple adder, it'll be 4 bits, and we will want, here's a thing that this is the 7-segment display that we played with in lab 2 and in lab 3. And that was also here under indicators, DCD hexage. Okay. And so here's this thing with 4 inputs. And then it displays a number. And what's important is that you understand that this is the ones place. That's the ones place. And that is the 8's place. Slap down some crazy label or something. So this was the ones place.
Is it like 1, 2, 4, 8 or?
Yeah, 1, 2, 4, 8. And so when you're connecting it, so where's the adder? The adder is under Miss Digital. Here's Miss Digital. I usually do this one, and then there's a half adder. There's the full adder. Here's the full adder. And if I have two full adders, you'll have 4. But if I have 2, I will take the carry out of 1 and make it the carry in of the next guy. And if it carries in this direction, then that makes this first one the 1's place and the second one the 2's place. And then if I were displaying, say, the output, if this is the 1's place, that would go here. And this is the 2's place, it would go here. And then you owe me 2 more. You owe me a 4's place and an 8's place. This is, you can say, I don't get it, I do get it, or can you show me some more?
80 and a little off.
You're a little lost. Let's make a new. I've got too much crap in there. You're gonna make a. Where's Miss Digital? Miss Digital full adder. You're making a 4. That was crappy. Not too crappy. Okay, there it is. Okay. So here are 4 full adders. If say this is the 1's place, the 2's place, the 4's place, the 8's place. Let me put a label. The 1's place. This is the 2, the 4. The 2's place, okay. The 1's place carries out and becomes the carry in of the 2's place. That's what we mean by ripple addition. I'm going to have the A, B, C, D, those are just inputs. They go to switches. That's a switch. I'll just draw the A's. So here's my A was red. Let me make this purple. So my A was red. And here's another A, and that should go to a switch, and that should go to a switch, and that should go to a switch. And that's the 1's place of A, the 2's place of A, the 3's place of A, the 4's place of A. Let's say I want to display A in a way that it will look like a number to you. I can use the hex display. Let me choose red because A's were red. And this was the 1's place of A, and the 1's place, and the display, this is the 1's place.
Wait, how did you get that one? I'm sorry.
I went to indicator, hex display, DCD. And this is the 2's place of my A's. This is the 3's place of my A's. This is the 4's place of my A's. Then if I did B's, I'm going to make them blue. B for blue. I wanted to display my B. I get another one of these guys. Let me take this guy. There. Let me take these guys, that'll be better. Let me take my adders. I'm going to push them over. I wanted to display my B's. Let me get a blue for my blues. Here's my B. Here's the 1's place of B. Here's the 2's place of B. Here's the 4's place of B. Here's the 8's place of B. And then if I want to display the sum, I'll make that the sum should be green, right? Humor me. Here's the 1's place of the sum. Here's the 2's place of the sum. Make those green. So this is the sort of logic. You have 1's place, 2's place, 4's place, 8's place. You carry from the lower place to the higher place. you have 4 switches corresponding. I didn't draw the switches because I'm lazy. You have the 4 switches coming into the A's, you have 4 switches coming into the B's, and then you get your answer is a 4-digit number. You're going to display the A, you're going to display the B, you're going to display the answer. So if we don't have overflow or anything like that, I should be able to see 3 + 4 = 7 or something like that. That's lab 5. But you had questions on lab 4,
Yeah, no,
and I got all distracted
No,
about
you're good.
display. But did I distract you from your lab 4 questions is my question.
You did, but it's
So-
okay, this was wonderful too.
But now take me back.
It was the,
So you had this guy,
yep, I
Oh,
have that.
you have that.
Trying to figure out what the
the sub-circuity thing.
subcircuit, yes, that was called.
So,
Yeah, I agree with subcircuit.
so let's look at this. Remember, remember when we had this crazy ass thing, the full ladder?
Yeah,
Okay. If I were going to turn that into a sub-circuit, I would drag a rectangle. And I would make sure that my rectangle cut. I'd make these lines longer to carry in the A and the B. I'd make those lines longer, go up higher. And I'd make a rectangle that cut this line, A, to carry in the A and the B. And cut this line to carry out in the sum.
oh, in one rectangle or two separate rectangles?
One rectangle.
Okay.
So let me see, I can draw, I think. It's almost like I planned it, I don't know. I would draw a rectangle like that. And can I get that transparent fill? I don't know.
No fill, wait, no fill.
No fill, okay, so here's my box, okay. I'm cutting this, I'm cutting that, I'm cutting that. That means my box is going to have little sticks where I can get stuff into it and little sticks where I can get things out of it.
Okay, I can visualize that, yeah.
So I want my inputs and my outputs to cross my box. And I don't want my box to cross anything else. So that would be a problem down at the bottom where I'm crossing things I don't want to cross. So I want to keep my inputs crossing the box. Anything else, any other stray stuff should be on the inside.
I think that's the simplest thing you've explained on that. That's, yeah, I follow that one.
So if you do that, then you'll create a sub-circuit. And this would be the sub-circuit, this would be the full adder. That box. If I had this circuit and made a sub-circuit, I would be making this box.
Yeah, fine, okay.
That's not what you're making, but that's the idea of you just sort of encircle all that's in the box. But you need to get some stuff into the box, you need to get some stuff out of the box.
Right.
Okay.
I follow. Thank you, that was, yeah. So use the address and then.
So then I force you to operate it. And you can operate the original if you want. If your sub-circuit thing didn't work, you can operate that.
Can I just draw it? Because I can just draw a box with a D0 at the top and a D0 at the bottom and
No.
in.
No, you have to actually make it in the system, but for the part where I'm saying this has got to be high and that's got to be low, you can either do with the original circuit or you can do with the sub-circuit. I don't care either way. Because they're both the same. But right now I am choosing A low and B high. So right now I am choosing A low and B high. I'm choosing this guy. And so what I ask you to do in the first one, what I ask you in that lab to do I have? No, I don't
Oh,
have.
you're asking us to draw a box around the specific. Okay, and then cut out through the,
So you would cut here. What am I doing? If I were here and if I were drawing the rectangle here, insert. Here's my shape. Here's my box. I want to cut 6 things. Two select, 4 data. Those are the inputs, and 1 output. That's the box I would want to make here.
okay. I found it.
That's the subcircuit.
That's a ring drawing.
And then I ask you to sort of start using it. Put in the address, put in AB of 0, put in low, low. And then you should be selecting data 0. And I say data 0 should be low, and you should see the output be low, the probe not lit. And then in part B, I say keep it at address 0, but now put in the data high, and the output should light up. And then I say put in address 1 and have it not lit up, and put in address 1 and have it lit up.
Okay.
What the circuit does, A and B are, you can have 4 combinations of A and B. 0, 0, 0, 1, 1, 0, and 1, 1. Corresponding to the numbers 0, 1, 2, and 3. A and B are 2 inputs, so there are 4 possibilities, and we think of them as 0, 1, 2, and 3. We think of 0, 1, 2, and 3 as the addresses of the data D0, D1, D2, and D3. So D has after it a number, and if A and B are creating that number, then that data is what should get through to the output. So if I am choosing, if I have A0 and B0, if I'm choosing the first data, the 0, 0, data 0, then I should be able to flick the 0 switch and see the light blink, and none of the other data switches should have any effect.
Okay.
That's what it does. It chooses something. So if the combination of A and B is how I choose. So if A and B are low, I am choosing 0. So data 0 is the one that should get out. And so if I'm playing with the D0 switch and flipping it up and down, I should see the probe lighting up and flickering, going on and off. And all of my other data should have no effect. If I put in high, high, I should get a 3. I should get data 3 is now the one who gets out. And so that one part of the lab, I'm just sort of forcing you in the beginning through working it. Choose the 0, choose data 0, and see if it's low, I get a low. If it's high, I get a high. Choose data 1. Use A and B to choose data 1. And then if data 1 is low, you get a low. If data 1 is a high, you get a high. You're just choosing who gets through. That's what a multiplexer is. That's all it is. Who gets through.
All right, no, I definitely know that.
The demultiplexer one thing comes in and you're deciding where it goes to. So in both cases, you're deciding. In one case, you've got a bunch of things and you pick which one gets through. And in the demultiplexer, you have a bunch of locations and you're picking where it goes. So in the final build for that lab, not the resistor part, but the final in lab 4B, the last part, there you have a multiplexer, it connects to a demultiplexer. I say pick one of the sources, I say pick one of the destinations, and you should be able to do that. You should use in the select or the address inputs of the first guy and pick whoever I told you to pick. And you should be able to use the address inputs of the output. They're not necessarily the same. And yeah, you should be able to pick the destination that I told you to pick. And if you can do that, then you understand multiplexers and demultiplexers, because that's all they do. They pick stuff. Yes, no, maybe.
Yeah, I'm gonna have to learn on. I mean, I get it, I just need to really.
Okay. Just that question, historically, when I give that question on the test, 3 people get it right and everybody else goes, I don't know. It's not hard, but people don't invest time into understanding it. So it just takes a little investing of time. But it is picking, you're picking. Multiplexer picks the source, demultiplexer picks the destination.
See, that I get, it's just, it's building it.
The rest is the building of it, but each one is on the slideshow. So you build it to maybe a little bit of thought about how to put them together, and then the picking.
You said we could build these ahead of time before the test.
Yeah. Anything you want to build, you can build. You can bring everything from labs.
Thank you.
Sometimes I give you things. I've been known occasionally to give you the resistor network, especially back when we were completely online and everybody had to like share a machine or something crappy like that. I would build the resistor network and you would just play with it. You'll probably have to build your own resistor, but
On line 3 part, can you show us how to build the circuits for like the expressions?
okay. Like if you had a sum of products or something.
Yeah.
Okay. So I have a thing called switches, and that makes life easy. Where did I put switches? So here's my switches. I probably have it already, but I'll bring it down again. And I thought this is probably some old version of switches, but as soon as I touch it with whatever multi-sim, it'll become the current version. So here I have A, B, C, and D, and the knots. So I've given you a good head start. And let's go back to, we were playing with this game. Let's build this guy. Let's build a max term. So that's, what do I want? I want three input OR gates. Right, the pluses are OR gates. I'm adding 3 things and then I'm doing it 3 times. So I want three input OR gates. Miss Digital. Here's the OR. I want 3 of them. And then they go into a 3 input AND. Maybe I'll stick a probe on the end. an orange, I'm in the orange mood, okay. So this part is easy. The ors just go to the and. The output of the and goes to the probe, and now I have to. Not that. It's here, okay. So what do I want? I want A plus B plus C prime. There's A. There's B, and then C gets primed. So that is this red. All the prime ones I made red. So it was not red, not red, red. Then it was A, B prime, C prime. So A for not red, but then the B and the C were red. And then A prime plus B plus C prime. So the A was red. The B was not red. And then the C was red again. And I didn't want the D. I don't have to take it. You don't have to take it out, but you could take it out.
That's what you want to see for the homework?
And that's, if I said, I didn't say on the lab to build that, but if I had, this would be the build, but I might say on the test.
Yeah,
I usually do.
for min, would you use the and?
These would be ands, yeah. And these would be ands, and this would be an or.
Okay, so you can flip off.
You flip them.
Okay.
Any other questions? And we'll do, what did we agree on? Like a half an hour of lab. You don't have to, if you don't need it, you don't want it, it would throw you off. Just show up at half an hour later, but 6:15 or whenever the hell I show up and you start asking me questions, but at least 6:15 to 6:45, I'll reserve to answer questions. And if you want to Zoom with me during the week, that's fine too. Or come and see me in the lab, whatever, however you want to ask your questions. Anything else for the recording? All right. I will stop recording.